Hello, folks. This is Sridhar Ramakrishnan. Welcome to this month's webinar, where we have Dr. Rick Sheldon talking to us about cybersecurity from Oak Ridge National Labs. Let's see, a few preliminaries. I guess the presentation will begin shortly and go on until about 1 p.m. Pacific time. Rick has agreed to stay on for a few minutes thereafter to engage in any follow-on questions or discussion. The slides and the recordings will actually be available at the end of the presentation. Please log into your Malibu account to view them. We do have a YouTube channel now, so you can actually go to our site and click from there into the YouTube channel. That's where Rick's presentation will be. And I think Rick is also going to probably put a link up on the Oak Ridge National Labs website to his page as well. Let's see, please keep your telephone or microphone muted at all times. Only unmute yourself to ask questions. This reduces the ambient noise of typing, cell phones ringing, et cetera, And as I repeated before, if you've dialed into the conference by telephone, you should enter your audio pin. If you don't, I have no way of unmuting you. This is a feature of the system, one that I'm unable to change. You can, however, ask your question by chat. Feel free to type in your questions, and I'll relay them to Rick. And he has indicated that he'd love an interactive session, so if you have questions, comments, discussion, please engage in them. If it's a question that needs to be better deferred towards the end, Rick will let you know. With that, let's go ahead and get started. Today we're delighted to have Dr. Frederick Sheldon to talk to us about failure impact analysis using Cybernomic analytics. Dr. Rick Sheldon is a senior research scientist in the Cyberspace Sciences and Information Intelligence Research Group at Oak Ridge National Labs. With 25 years of plus experience in the field of software engineering and computer science, Dr. Sheldon has held faculty appointments with research universities, including R&D positions at 3 Fortune 100 companies, and was a postdoc visiting scholar at NASA, both Langley as well as at Ames, Stanford. He has published over 100 papers and edited 6 books with developing and validating models, applications, methods, and tools for the creation of safe and secure dependable systems. Dr. Sheldon is a co-inventor on several patents, senior member of the IEEE, received the Sigma Chi Outstanding Dissertation Award, as well as several key contributor and significant awards from ORNL, UT Battelle. Dr. Sheldon holds 2 Bachelor's of Science degrees from the University of Minnesota and a Master's and PhD in Computer Science from the University of Texas in Arlington. On a personal note, I actually met Rick when I was at University of Florida, the NSF event on autonomic computing, where Rick actually chaired a panel discussion. And in the course of lunch, the topic of the day was, at that time, the current information about Stuxnet. You might recall that that was a virus that had infected industrial controllers with the idea of affecting nuclear reactors using those particular brand of industrial controllers. And at that time, Rick mentioned that one of the charges that he had been asked to look at, or at least the lab had been asked to look at, was how do you protect the nation's energy infrastructure, both from a cyber perspective as well as a physical perspective. That sort of continental or galactic challenge was sort of really interesting, and we had a good discussion about that. So I'm actually delighted that Rick is actually going to talk to us today. With that, I guess let me turn it over to Rick.
Thank you, Shrid here. Shrid here. Sorry about that.
Yeah, that's fine, Rick. Go ahead.
I thank you for that. Very nice introduction. And this project, this talk is about. It comes out of a project that was funded by the Office of Electricity, and we are developing. We've got a bit of an echo going on, so I'm getting a little confused here. So let me see. I don't have a headphone.
Rick, don't worry. I have muted folks, so I think, are you okay now?
Yeah. Okay. Yeah.
Okay.
I think so.
Okay.
Let me
go
continue.
ahead.
All right. So this is a centralized cryptographic key management project that was funded by the Office of Electricity at DOE, and it's a industry-led project that involves Cypress Electronics as the lead, and EPRI, and Purdue University. So I'm going to talk about work that we did to evaluate the cryptographic key management system within the automated metering infrastructure. I just wanted to mention a little bit about the notion of Cybernomic. We've used cybersecurity econometrics as a way of describing our model, but they're back in about, well, the date is unclear actually. Merrill Lynch supported a 12-page essay by John Perry Barlow on Cybernomics toward a theory of information economy. And in that, Barlow talks about the consequences for the information economy. He says that relationships replace things. He goes on and talks about, it is a never-ending marvel to me that people have such a difficult time dematerializing their thoughts about commerce, moving beyond the trade of things, when so much commerce is a post-industrial economy, in our post-industrial economy, is already based on intangible relationships. And he goes on and says, the real curiosity here is that we continue to quantify these relationships as though they consisted of things, generally units of time, and in most cases, time is of little relevance to actual value exchange, which is more often expertise or insight. But it is, of course, very difficult to put a number on insight. And so actually, the whole purpose behind this cybernomic situational awareness is to gain insight into what is going on within our networks, within our critical infrastructure. And I think that's underscored by the current events that have been occurring on a daily basis that we hear about in the news. So let me move on and sort of lay out the framework and then talk about an example that sort of shows how we've tried to apply this model to understanding how this cryptographic key management system can be effective in protecting the distribution system, at least within the smart grid. So, the subject domain of complex systems and risk management, the introduction to current needs in the smart grid are really, the basis for what we try to formulate as a framework to evaluating this complex system. And what we come up with is a mean failure cost, which is really based on years of research in the domain of dependable systems. So we have a computational infrastructure, and we use information about security requirements, system stakeholders and their stakes in the system, their missions, system architecture, the dependencies between the components that make up that infrastructure and architecture, and threat configurations, so to speak. And so, in applying this model to the smart grid, to the AMI, we utilized documents including the NIST 7628 and a draft IEC standard Part 9, which talks about key management. And then I'll talk about some conclusions we were able to draw in some future directions. So, a complex system is a system composed of interconnected parts, and that as a whole exhibit one or more properties, behaviors among possible properties, that are not obvious from the properties of individual parts. So risk management is something that organizations typically use in dealing with complex systems to identify and mitigate risks and to assure their organizational mission. So risk management provides a documented, structured, and transparent process to identify critical resources, estimate threats and vulnerabilities that may intersect to cause harm to those resources or assets. So the current needs of the smart grid are very well documented within the roadmap that was published to secure control systems in the energy sector. This plan provides a supporting framework of goals and milestones to protecting control systems for the foreseeable future. The tagline for that document is really resilient energy delivery systems that are designed, installed, and operated and maintained to survive a cyber incident while sustaining critical functions. And so for the cybersecurity econometrics model, the main measure is the measure of mean failure costs. We need a logic for specifying requirements and verifying secure systems against those requirements. We need a model for managing system security by quantifying costs, risks, and measures, countermeasures, and for estimating return on investment. And some tools that support this whole process of accounting for all of those factors.
Rick, I have a quick question here.
Sure.
I guess I just want to get some context around this MFC. Is the mean failure cost associated with sort of components of a large system? I mean, what's the granularity at which you estimate or compute the MFC?
Well, the granularity starts with the various stakeholders. So each stakeholder has at least one mission, or call it a requirement, that they're trying to satisfy. And so the most interesting part of the model is trying to understand what's the failure cost associated with not achieving that particular mission or requirement.
I see. So it's not the failure of a systems component like a disk drive or a computing center. It's actually failure at the requirements level.
It can be tracked down to that. So we want to understand what particular components are necessary in fulfilling that mission. So we can really understand when those components fail, whether what requirements will fail. And actually, I know that as we get further into it, you'll see exactly what I mean with matrices that account for all of this, and that's kind of going to fall out of it, I think, as we go on. So let me defer that question, and if it's unclear in just a few minutes, I think we can go over it some more. But I just wanted to really provide a basis, a premise up front before we get into the math, which isn't too difficult. It's pretty straightforward, and I think that it's very intuitive how it accounts for all of those components that are necessary for satisfying those missions that I spoke of. Now, up front, I'd like to say that one of the goals of this system, of this model, is to provide a quantitative indication of reliability and performance and or safety of the system, accounting for criticality of each requirement as a function of one or more stakeholders' interest in that requirement. So the way it's designed is that stakeholders share requirements. They also share components within the infrastructure. And in the case of the smart grid, we have in our example, we identified industrial type stakeholders and vendors that provide equipment that are components within the infrastructure. So I think that'll become clear as we go further. And also, you know, the insight that is gained from doing this provides a basis for choosing different courses of action that may reduce the most risk for the lowest cost. And that's because mean failure cost is a bottom line type metric. It's dollars and cents. So you can compare different risks, and you can rank threats, and you can understand which failures that might be caused by these threats would be the most impactful. So in that way, you can prioritize your courses of action. So MFC reveals how much each stakeholder stands to lose from mission value due to requirement or component of that system failing. It's not intrinsic to the system, but it varies by stakeholder. So to estimate the MFC, we need a set of stakeholders, a set of requirements. For each stakeholder and each requirement, the stake that a particular stakeholder attaches to that requirement. You know, what is the value of that mission within the context of the entire organization? To take kind of a militaristic view, I mean, every warfighter is got his own mission operational definition, and it all fits into the big picture of any particular movement or mission that's underway. So also, we need to understand, or at least have some information about the likelihood that the system provides the service as specified. So, you know, what's the likelihood that a component would fail, or given a threat to that component emerges, would fail? So, you know, this was one of the first pictures we came up with, and I hesitated to throw this in here, but I think that you know, it gives a baseline view of the 3 stages of, or 4 stages really, when you talk about at the end you have these mean failure cost values and return on investment calculations. I mean, you have this discovery, evaluation engine, and metrics engine, and when you look at the big picture, you begin to see that, whoa, you know, our critical infrastructure has many different stakeholders in it, and we need some way to estimate their stake in the infrastructure, and then we have all these various dependencies that exist within, you know, as far as components and their function and interaction within a network of grid components, for example, and as well as the dependencies that exist between requirements and those components.
And some of these very qualitative metrics that people will come out with, you're trying to convert these qualitative metric into a quantitative metric?
I think that's a good way of describing it. Is you know, in fact, when, you know, the way we've structured it is in our tool is to provide a sort of a baseline stake for each stakeholder that, you know, you want to be able to sort of normalize among stakeholders their inputs into these stakes, and so you provide a baseline, and then as you go on in time and you refine this, you continuously revise those numbers. And it's kind of like, I liken it to what the insurance industry does. I mean, they're constantly evaluating these assets and their value and the possibility of those assets being damaged in some way. And so, you know, we're trying to do the accounting of stakes and components and how much those components actually contribute to satisfying those requirements that represent the stakes, and also not really having a good understanding of the threat space. I mean, you know, this is something that sort of is very dependent on historical data. The one thing we typically in the grid, we have a pretty good understanding of vulnerabilities. I mean, there's a lot of legacy equipment in the grid, and there are a lot of you know, a lot of operational experience, and yet there's plenty of vulnerabilities that are unknown. So, but those are the things that we're trying to account for in this model. And so that's kind of the purpose of this picture, is to kind of establish all of the components, all the parameters within the model, and in fact then we need to understand what the impact of those threats would be, and without knowing what stakeholders would be impacted by those threats, I don't think we can accurately understand the total impact to the organization. So this is the picture. It's one of our early ones. This picture here kind of tried to more concretely identify the components that you know, we would imagine that in fact we would have, for example, case histories of anomalies that would be factored in. We would have threat scenarios, and we could look at, for example, the set of CERT case histories of different malware and insider threat and so forth, and you know, just a comprehensive catalog of threat behavior indicators, so that column of blue bubbles represents, you know, a brain dump of all the potential inputs that we would want to qualitatively account for in some way, and trying to come up with a more quantitative, hard number of mean failure cost. And then, you know, the components in orange there include the various matrices that we needed to populate, which I'll be just getting to in the next slide here. So let's look at the stakes matrix. We have the stakeholders on the left-hand side row-wise and requirements column-wise, and where you know, the premise is that, you know, a stakeholder may have different stakes in different requirements, and a requirement may carry different stakes for different stakeholders. And so the whole idea is, let's look at how those two things intersect and identify the cost that a stakeholder would lose if the system failed to meet a particular requirement. And that's what you see as the FC I sub j element in the matrix. And so the mean failure cost for a particular stakeholder, S sub I, is equal to the sum of those failure costs times the probability that a system fails to meet a particular requirement. So now what we need to know is what is the probability that a system fails to meet a particular requirement. And that we get out of the dependency matrix, which is requirements versus components. So the probability of requirement R sub I failing is shown here, and it's determined on the basis of the probability of failing requirement R sub I giving component C sub j, given that component C sub j fails. So, and those are the numbers that need to be accounted for in the matrix, in the dependency matrix. Now, those numbers are hard to come by. All right. And in my example, I'll kind of show you how we tackled that issue. It essentially boils down to a matter of balancing a budget of probability across all the requirements for each component. So you know, this matrix links the probability of failing a particular requirement with the probability of a failure of a component of the system. And the hypothesis is that we assume that violations affect no more than one component at a time, and that that E sub I is the event that component C sub I fails, and the event E sub k plus 1 is the event that no component fails. And that'll come into play when you see the example. Now the impact matrix, which is really the last matrix in the computation, is components versus threats. And inside of that, we're looking at identifying the probability of a component C sub I failing given that threat T sub j materializes. Okay? You know, there's something implicit in this model that isn't really explicitly described here, and that is the vulnerabilities. And a lot of people have been concerned that we're not explicitly accounting for the vulnerabilities of these components. And in fact, we have been implicitly considering those in the probability of a threat materializing, which is this vector that you see at the end of the equation, which is determining, you know, the probability of component C sub j failing. Given that E sub I, which is the event that that occurs that causes that component to fail because of the threat materializing. So bringing all those equations into focus, you see that we have the mean failure cost computation in the second row here, and it includes the probability of a requirement failing, as well as the impact matrix, which includes the event of a threat emerging and actually causing a component to fail. And the PT is the vector of threat emergence probabilities. So I know that was a quick overview of the math, but it provides the basis of doing all of this counting. And so for looking at the cryptographic key management alternatives, we're looking into, as we see how that management system is, the topology of that system, we expect to be able to provide some costs and benefits of different approaches, or different sort of hierarchies of establishing head ends and the number of subordinate smart meters that are attached to those head ends. And we want to be able to quantify the impact of failures. We want to be able to offer some decision support for security countermeasure design. We want to be able to distinguish between stakeholders, components, and different degrees of assurance. So what we did is
Rick, I have a question.
Yeah, sure.
Is there a sense in which there is a learning component to the system? I guess the analogy you used earlier was the insurance analogy, which I kind of like. In the sense that underwriters are always trying to sort of figure out what is the actual probability of a risk, and making sure that they underwrite the costs so that when that event does occur, they've actually got enough money to pay for the for that particular threat as it emerges. So in this particular case, in your system, if I would use a similar analogy, the cost gets paid at the time the threat actually materializes, right?
Yes, I mean,
and so how
the impact occurs at the time that the system fails.
Right. So in your case, is there sort of a feedback loop here in your graph where there is some failing that is occurring, and then you sort of go back and tweak the matrices, so that those costs actually then get truly get reflected. That is, when the actual event occurs, there is an actual cost that takes place, and then you sort of go back and figure out what was the actual modeled cost, and then you sort of correct. Is that how the system sort of learns?
Yeah, I mean, you're stealing my last slide, essentially.
Oh, I'm sorry. I'm sorry.
No, that's all. No, you're right on, Sridhar. The basic idea is that you need to collect this information. So when you have a failure, you need to understand what it costs to mitigate that failure or recover from that failure. Either way, so that you can feed that back into the model and refine it, make it more accurate. So it's a living model of the system, and it's a basis for determining impact to the highest degree possible, given the collection of historical data that you can include in it. So obviously, if you put this in place, you want to continue to do that feedback loop that you just described.
But for any large system,
yeah, go ahead.
Like the ones you guys deal with, I'd imagine that the matrices by themselves will, I guess it may be hard to know a priori what the threats are, or the components that will fail are, or even the requirements, right? So I'm assuming even the matrices keep evolving over time.
Yes, indeed. And that's kind of, I don't have a demonstration of the tool, but that's the idea in creating the user interface, is to have these values constantly being updated as time passes. But for so in this particular example, I mean, we looked at three basic requirements: that of confidentiality, integrity, and availability. And that's what this slide is talking about. Is these are sort of high-level driving requirements, and they're all relevant to the grid, and they come out of this code, this U.S. code that defines information security as a means of protecting information and information systems from unauthorized access, use, disclosure, disruption, modification, or destruction in order to provide CIA. And I think we all pretty much understand what those mean. And you can read it here. And so, you know, in doing our requirements, those are the ones that we are imposing on the AMIs and the cryptographic key management system. So for confidentiality, we ensure that only authorized parties are able to access the cryptographic keys, and a loss of confidentiality could result in unauthorized parties gaining access to any information that is protected by the key, including but not limited to PII about a customer and a customer energy usage data. So, and then integrity is the idea of ensuring that the keys are not altered by unauthorized parties. So a failure of integrity may result in such consequences as power loss to the customer, to the meter. And then the availability is obviously a similar consequence, but the notion is that cryptographic keys are available whenever needed. And so when that is not met, possibly would result in loss of power. Now, you know, for the stakeholders, we identify these 5. It's kind of based on the NIST 7628 guidelines, a public power utility, an AMI vendor, a CKMS provider, a corporate customer, and a critical infrastructure customer like a hospital or traffic control, ground or air. Now, so how do we fill up the stakes matrix? Well, you know, it turns out that it's not; these numbers aren't necessarily readily available, but there's been a lot of, you know, in the last few years, because the Department of Energy has been really been very proactive in providing funding for research and development for the smart grid in grid modernization. You know, there's a lot of open available information that we were able to access in order to come up with rough guesstimates of what the failure consequences would be for these various 3 requirements against those 5 stakeholders. And you know, these are not hard numbers, as the earlier question was talking about, bringing qualitative information onto a more quantitative matrix. And on the right-hand side, you can see that the cost of no failure is 0, which is an important element to include for normalization of all of this. So, you know, the most prevalent, or the most costly, I should say, cost is confidentiality in terms of the cost to a utility or a vendor or of either the meters or the CKMS in our analysis. Now, you know, these numbers we had a couple of Katie and Margaret spent a couple of weeks doing some internet analysis, and this is the data that we vetted through that process. You know, for the various components of the system, we use the NISTer description of these components. So category 13, 14, 15, 16, 17, and 18 describe these components. Systems that use the network, systems that use the AMI network for functions that require high availability. Category 15 in the NISTer is systems that use customer site networks, 16 being external systems as well as the customer site, and category 17 are systems in mobile field crew equipment, and then finally category 18 is the metering equipment itself. So given those requirements, we have the dependency matrix shown here that identifies the requirements on the left-hand side and the components across the top, and of course we have the normalizing column of no component failure is the case when a component fails but does not affect the associated requirement. And if you do the math, you'll see that the NRF row at the bottom is added in, and it reflects the fact that we expect that no requirement would fail, as in the case of category 17, 40% of the time, and it all adds up to 1 column-wise. So the next question is, in determining the threats against the AMI system, we looked at the draft Part 9 of the IEC 62351 series, which specifies how to generate and distribute, revoke, and handle digital certificates, cryptographic keys to protect digital data and communications, authentication, etc. And so this is the life cycle of key management, and we have 13 threats, a threat to each and every step within the life cycle, as well as T13 as being no threat. And when we look at the impact matrix, which is the threats versus the components, we see that we have all of the threats across the top, and again we're adding in this column, or I should say row, that represents the case when a threat materializes but does not affect the associated component. And then the column on the right is no threat column, represents the case when no threats materialize. And again, you can kind of see by the numbers that this is a baseline estimate of the expected probabilities of these components being affected by these threats. And it's something that needs to be monitored and updated as things happen, and to improve the precision and accuracy of the model itself. And then finally, the threat vector, which involves the 12 threat categories, is shown here. And you can see the probabilities of a threat materializing on a per-day basis. And no threat is the highest of all of them. Most of the time, no threat materializes.
And I guess this probability comes how just looking at historical data?
Yeah, in this the threat vector, Margaret and Katie were trying to find information on this, and I was not present at that time, and I do not know what the source data was that gave rise to those numbers. I apologize for that. These are fairly low numbers. Now, if you look at the numbers comparatively, key registration is the one thing that they determined was the most vulnerable to compromise. They've given it 0.1 as the probability of every day, 10%. So every 10 days, there's a compromise of the key registration process. Personally, I think that the numbers would be much smaller. But when you're interested in seeing the computation from MFC, you want to keep you want to see the numbers varying, and you want to see them all in the same order of magnitude. Otherwise, you get a rather brittle model, and things the numbers don't change much at the end. So these numbers are, in my view, a little high, probably a couple more orders of magnitude, if not more. It's my personal view that these are rather rare events that keys get compromised. So in the end, the mean failure cost for each of the stakeholders that we identified looks something like the following. So the utilities versus the AMI vendor versus the CKMS provider, and a corporate customer, and a critical infrastructure customer. And I think it gives insight. I mean, it's kind of the idea that we wanted to understand the relationships, as I was mentioning when I first started talking about the essay that Barlow was made when he talked about relationships replacing things, and understanding which impacts, which stakeholder will be impacted the most. Obviously, in this case, it looks like when we looked at the AMI, the key management system provider mean failure cost would be the highest. Now, let me just kind of go through these conclusions. I mean, we're close to 10 minutes to the hour, and I just wanted to kind of give you the general conclusions, at least in at this point in the process. We're trying to, well, let me start at the top. We use these existing standards and guidelines as a basis for developing the mean failure cost for those specific stakeholders within the AMI environment. And then the numbers we need are not generally available in the public domain, but as such, we rationalize the establishment of initial values that are needed from information that's readily available and open. The vendors that are already providing smart meter services should begin keeping the kind of data that we would need to better predict the costs, the impacts of compromise. And obviously, as I was saying before, the stakes matrix is probably the most interesting to populate. It involves all of the stakeholders estimating their stake in the infrastructure. And for this project, we considered the possible outcomes for the failure of requirements CIA, confidentiality, integrity, and availability. And we then referenced information about the effects of those outcomes on entities similar to the stakeholders that we identified. And then the other matrices required more estimation based on empirical operational knowledge of the components. So we approached their population from a budget balancing point of view to better gain insight into what the mean failure cost was for each of the stakeholders. And in terms of the future, the team intends to have access to subject matter experts in assisting in determining those values. As I said earlier, we're interested in the insight, what components and what functions, what requirements are the most sensitive, and we are, the example described here only accounts for a small number of stakeholders. So we're also interested in, one second here, somebody just desperately wants to call me. The examples that we used were cherry-picked from a list of 29 failure scenarios, and we picked 5 out of the 29, and so we need to more fully address all of the various failure scenarios and additional requirements such as no unauthorized access, sustained operations, and more specific, going upstream to the control systems and the head ends and substations and control center sorts of things, that all of which have been defined in the NISTR 7628. And then future analysis need to be more comprehensive in terms of establishing energy delivery systems threat models that exist already. There's a lot of information that potentially can be tapped into in terms of better estimating threat emergence probabilities, and in talking to utilities, we feel like we could get more accurate data in populating those other well, especially the threat probability matrix. And then finally, in absence of that information, what we have done as kind of a workaround is we've been evaluating a game theoretic simulation where we have active defenders and attackers, and so we actually just finished a paper that we submitted a couple weekends ago, and that just talk about the probability of an attacker's success in getting through all the various steps that are described in the failure scenarios for the AMI, and so we're in the process of trying to link up the Cybernomics or the econometric model, the mean failure cost, with these games that show the interaction between the defenders and the attackers, and so that's where we're headed for the rest of probably this year, is finalizing our understanding of how agent-based simulation can help us better understand the full spectrum of possibilities in this very complex system, and also try to solicit more subject matter expertise in zeroing in on more accurate numbers, and at least understand the relative importance of different key choke points within the AMI, and the impacts of compromise of those choke points. And I guess that's about it. We're gonna be we're in the process of building a website called cybernomics.ornl.gov, and we're going to be, we'll be putting the tool, making the tool available on that website. I'm not exactly sure all the intricacies of how that's going to happen, but there'll be a lot more information out there, and I'll put a link to the YouTube video of this talk up there, and that's about it.
So Rick, thanks. I guess before there are questions, I guess the first thing I want to say is the next talk will be on July 26th by Arifan Hassan from the University of Illinois, where we'll be talking about session management of 3D collaborative applications. And so for those of you who need to leave immediately, thank you so much for attending. We'll see you on July 26th if your time permits. I guess with that, maybe we can have questions for Rick.
Yeah, I had a question. Have you run this model by any utility company to see how receptive are they in giving these numbers? Because in order for this model to succeed, you have to populate all those matrices, right?
Yes, yes. The answer to that question is no, we have not. And that's kind of an important question. And I think by establishing our website and so forth, we hope to be able to get more interest in experimenting with this. We've been putting forward proposals that would allow us to have more funding to approach those utilities as well. I mean, one of the projects that I'm involved in is involves utility participants from across the country, but it's not the main topic of discussion. Lately, what's been funded in these has been the process of critiquing the standards and providing guidelines. One of the teams that the NESCOR group is supporting is actually responsible for the failure scenarios, and there has been a little bit of discussion about how do we understand the impacts of these scenarios amongst the group, but we've really had a hard time making progress and getting a lot of participation in that on a voluntary basis. So I think if we're going to get there, we need some solid commitment funding to get those numbers into the model, and it's still an open question as to whether we will really have the support we need to do that. But obviously, it would be an important next step.
So there's a question that is coming online, Rick, and I think maybe it's related to the previous question, which is how would you test whether this model works?
Well, I think, comparing the output of these, mean failure costs for the various stakeholders with against, these two ways, really, looking at the failure scenarios and sitting down with the subject matter experts and the asset owners and doing a real, running through tabletop sort of discussion about what the cost would be, and then comparing it to the output, and then trying to just work through and improve the numbers that are used internally in the model. The other is to just baseline the model and wait for things to happen and account for all the costs, the recovery costs, the mitigation costs that are involved. I imagine that this would be really useful within the organization. So in the hands of the asset owners, the utilities, actually, I mean, this is, so if you look at the IT enterprise type analogy of this, this is something that we do internally at Oak Ridge National Lab, is we have a very good handle on all of our computational resources, for example, and what patch level they're at, and what vulnerabilities exist, and this has been it's been a long process, but we're getting a much better handle on mitigating all of the various vulnerabilities that have caused us problems in the past. And obviously, as we all would agree, in many cases, it's not so much the technology as it is the highly informed insider that walks off with a flash drive full of secret documents that ends up being the most costly. But yeah, I mean, the insider threat is one that we can account for in the model, and so this, I'm a scientist, and I was asked to work on this problem of cyber economics, and so we came up with this model that it tries to account for all of the important aspects of the costs, and I mean, it's quite interesting how, if you look at what has been done in the past 20, 25 years in terms of dependability theory, it's just it follows along the same process. It utilizes the same kinds of relationships and mathematics as has been existing for many years. In terms of reliability, availability, it was a long road for us to really get a handle on that, and indeed, I think it's been effective in improving quality of service across the industry, and so I think this is a very fundamental thing that needs to be promoted, and I think eventually we're going to see a lot more interest in really nailing down the fundamental costs and rationalizing the investments that are necessary to hardening the infrastructure. The folks in the McAfees and the Symantec's in the world are well familiar with the process of selling something so that nothing happens. It's a hard thing to sell, and so we try to identify, and we have a paper that describes return on investment in this context. To sort of show that we can allocate the costs of hardening the infrastructure according to those that have the most to lose, that stand the most to lose. And I think as we go forward, that I would like to talk to you if you have any insight on, in terms of, or partners that or if you are a utility and are interested in finding out more about the model and how we've applied it in this project. So certainly feel free to contact me if you want to discuss it further.
That's great. Any further questions for Rick? I guess if there are none, Rick, one of our customs, as you might have seen from previous webinars, is to sort of do a virtual clap. So I guess for those of you who are still online, please unmute your phones and extend Rick a warm virtual clap here. So thank you, Rick, very much for this great presentation. At the end of this talk, we will have the video as well as the slides available to all. And I think Rick did mention for folks who are in the utilities and might be interested in some of the smart meter stuff to reach out and connect with Rick to sort of bring maybe an industry perspective as well to that. So with that, thank you very much, Rick. Thank you all for participating. See you all on July 26th. Thanks. Bye-bye.
Okay, thank you. Yep.